enjoyed the lectures, this is really interesting stuff, but I don't think it's right. I've decided I'm going to start working on this. So Einstein spent 8 years of his life working on gravity. No one else has cared. Suddenly he's realized that most of what he's done is wrong, and now he's got competition, and the competition is the greatest mathematician in the world. Einstein's not very happy. He gets depressed for a little while, then suddenly he sort of shakes himself out of that, and he decides he's just going to do this. And he sort of launches himself into this work with a focus, an intensity which is maybe unrivaled in all of human history. He forgets to eat. He just spends all his time trying to solve this problem about gravity, and it goes on for months. It's not just a few weeks, it goes on for months and months and months. Finally, it gets to November 1915, and Einstein has agreed to give a series of lectures at a place called the Prussian Academy of Sciences. So this is a meeting place in Berlin where all the best scientists in the world get together. Einstein's meeting a series of lectures 1 week on his theory of gravity. He originally was back earlier in the year because he had a theory of gravity, but now stand up in front of these guys, he's got nothing at all to tell them. So he comes enough together just to give the first lecture, and from then on, he's kind of working in real time. He has to spend his week trying to solve this problem which he struggled with for 8 years. At the end of the week, he stands up in front of the Prussian Academy and tells them what he's figured out that week. Finally, 2 days before the last lecture, he cracks it. And when he's got it, this equation is just so perfect and so beautiful, there's no doubt at all that it's right. So on the 25th of November, 1915, Einstein stands up in front of the Prussian Academy of Sciences and announces to the world the theory of general relativity that he figured out 48 hours before. This is what he told them. You won't probably know one of Einstein's equations. Einstein has loads of equations, but his famous one is E equals mc squared, right? It's this beautiful little equation. This is the one that physicists really mean when they're talking about the Einstein equation. This is what they have in mind. I'm going to tell you briefly what it means. This is pretty advanced. You know, I said special relativity you learn in the first year of an undergraduate degree. General relativity you learn only at the very end of a degree. I think this is the most advanced thing we teach to physics students, the most advanced mathematics we teach to undergraduate physics students. So let me give you a sense about what this equation is. This is a picture of empty space. So before Einstein, we kind of had this vision of empty space as a stage on which the laws of physics play out, just a place in which stuff happens. And Einstein's great insight was to realize that that's not what empty space is like. Empty space isn't this passive thing in which stuff happens. Space is dynamic, and if something happens in space, space responds to that in some way. So here's a way to visualize it. This is what happens if you take something heavy, like the Earth, and you put it in space. So if you do that, space, as I said, responds, and it kind of bends and warps around the Earth. So it's no longer flat, but somehow space and time gets curved around the Earth. Then you take some other object, like the Moon, and you roll the Moon past the Earth, and the Moon feels the way that space bends and curves due to the Earth. And it's just like a marble rolling in a bowl. The Moon starts to bend around the Earth, just responding to the way space and time are curved. That's what we call the effect of gravity. It's not, as Newton thought, some force between two objects. What we call gravity is heavy stuff distorting space and time around them, and other heavy stuff reacting to the distorted space and time. This was Einstein's great vision of the universe. How am I doing? I'm going to tell you a little bit of the mathematics behind it. It might be a little too hairy, but I'll tell you a little bit of the mathematics behind it. Before I do this, let me just give you the punchline of the talk. So I said at the beginning, if you take away one thing from this talk, it's that general relativity is a theory of gravity. If you take away two things from this talk, it's that general relativity is a theory of gravity, and what we think of as gravity is space and time bending due to heavy stuff sitting there. Let me, I'll spend 5 minutes with a bit of mathematics, and then we'll move on to some good pictures. I'm going to try and explain to you how you write down the mathematics of curved space. Okay, and I won't quite get to that equation, the Einstein equation, but I'll tell you the kind of things that we're talking about. Suppose you've got flat space. Okay, so here's a picture of flat space. Here's some axes, and here's some coordinates on axes. So any point in three-dimensional space you can specify by giving me 3 numbers, the x, y, and z coordinates of that point. So here's a point x, y, and z. Okay. Suppose there's a nearby point here, which has slightly different numbers x, y, and z. And to show you that they're slightly different, I'm going to call this x plus delta x, but the delta is supposed to mean this is something. Okay? And y plus delta y, z plus delta z. And then the question I want to ask is, what's the distance between this point and this point? Well, this is something Pythagoras knew. This is just, the distance squared is delta x squared plus delta y squared plus delta z squared. So the distance is the square root of the right-hand side. Okay, that's how you describe distances in flat space. What happens if space is curved? So suppose, just for a simple example, we take a sphere. How do you describe the distance between 2 points on a sphere? Well, you're not allowed to take a shortcut through the middle of the sphere. You're obliged to kind of go around the surface of the sphere. So it's a sensible question. What's the shortest distance between here and Paris? You don't get to bury through the Earth, you have to go around. How do you describe that mathematically? Well, you do the following. Firstly, here's the sphere, and firstly, you need a way to specify where you sit on the sphere, and so for that you introduce some coordinates, and the coordinates we're going to use here, theta and phi, are basically what we call, I always get these wrong, but latitude and longitude, and one was latitude and one was longitude. I think longitude is the going round one. So you start at the North Pole, and you introduce some angle theta, and theta tells you how far you are from the North Pole. So theta equals 0 is here, theta equals 180 is here, or if you're used to radians, this is theta equals pi. Then you can spin around, and there's some other angle that I'll call phi, which tells you how far around you are. So this is the way we measure the other one, longitude. So phi equals 0 is said to be where Greenwich is, just for historical reasons, and then moving phi from 0 to 360, you go around the Earth. Good, so let's take some point on the Earth, and some point that's close by, And what's the distance to get from here to here? Okay. So how do you do that? I'm going to sketch how you do it. Firstly, if you've got an x, y, and z axis buried in the middle of this sphere, this is how you figure out, given an x, y, and z coordinate, where you are on the sphere. And if you sum up x squared plus y squared plus z squared using cos squared plus sin squared is equal to 1, you'll find that the sum of these squares is always equal to r squared, which is the statement that this defines a sphere. So the way you work this out is the following. It's some kind of differentiation. And I think, given the time, I'm just going to tell you the answer and then let you think about why this might be. Suppose you move from some point here to some other point by some small amount delta theta and delta phi. The question I want to ask is how far do you move in x, y, and z? And I've written the answers here, and you can see it's very closely related to differentiation. How many people have seen differentiation? Perfect. So x is a function of theta and phi, and you see that the amount you move in the x coordinate is, it's as if I differentiated sine theta, which differentiates to cos theta, times delta phi, and as if I differentiated the sine phi, which goes to plus cos phi, times delta phi. So, as I said, I'm just going to sort of leave you to think why differentiation might possibly be important in this. But these are the answers for if you move a little bit around the sphere, how much you move in the x, y, and z directions. Once you know that, you can figure out the distance squared, because you know the distance squared in the x, y, and z directions, because that's just Pythagoras. So plugging this formula here into this, and again, everybody has the sine squared plus cos squared equals 1 quite a lot, you find out that this is the distance in a sphere. So let's try and understand why that is. So here's a sphere, and theta equals 0 is up there, and here's the equator. And what this formula is telling us is that if you move a little bit in the delta phi direction, that's a little bit around, the amount you actually move depends on where you are coming down in the theta direction, because there's a sine squared theta here. But that makes sense. Suppose you move 1 degree around the Earth, so that's 1/360th of the way around the Earth. Then if you're on the equator, 1/360th is a further distance than if you're up here, just because these circles shrink as you go on. If you're on the pole and you move 1 degree around, you don't move at all, right? There is no mean to phi of your pole. If you're shifting phi, you just stay where you are. So this is the way that we describe distances on a sphere in terms of theta and phi. Now, what Einstein realized is the same thing is going on in space and time itself. That if you want to describe space and time, distances aren't described by this Pythagoras x squared plus y squared plus z squared that the Greeks thought of. It's much more complicated, and it's something with weird extra factors here and there. So I'm just going to flash up very quickly what I won't explain it. This is the distances in space and time for a black hole, or it's actually also the distances for space and time around the Earth. So this is, I'm just going to move on. This is a black hole. Let me finish with the story for the last 5 minutes. It's been 100 years since Einstein came up with general relativity, and we've just got overwhelming evidence for this theory. It explains the more accurately the motions of the planets, it explains how light bends around stars, it explains how time warps and slows down. We've done experiments to test that. It explains how the universe expands, why the universe expands. Of all these things, though, there's one prediction that Einstein came up with 100 years ago that we haven't yet got any direct evidence for, and it's something called gravity waves. So the idea is the following: if space and time is dynamic, then rather like if you drop a stone on the surface of a pond, you get these waves coming out. If you do anything dramatic in space and time, there are ripples of space which move away. So if I'm here on stage and do star jumps, I create little ripples in space and time which propagate out at the speed of light. Okay? They're so tiny you can never measure them, but there are much more dramatic events in the universe where we would hope to measure them. We have stars exploding in our galaxy, we have black holes colliding, we have neutron stars colliding. This is a simulation of two black holes which are spiraling into each other and will ultimately collide. We understand from Einstein's theory how many gravity waves, these ripples, that they emit. And we're now at a stage where we're building experiments which should be able to detect these gravity waves. So the best experiments we have are in the US. They're called the LIGO experiment, L-I-G-O. There are two of them, one in the state of Louisiana, one in the state of Washington. They're kind of astonishing. They're two buildings at right angles, and each building is about 2.5 miles long. And in these buildings, they fire laser beams backwards and forwards, constantly measuring the size of the building. It's 2.5 miles, 2.5 miles. But measuring the size of the building to about the accuracy of the width of an atom. So it's pretty incredible. What happens is these gravity waves from black holes in space or exploding stars, if they were to pass through the Earth, the entire Earth would just sort of shrink a little bit and then breathe out again. And these experiments are going to measure when that happens. At the moment, this particular experiment is closed down. It starts again later this year, and we think it's really going to have the sensitivity to detect these ripples of space-time moving through the universe. Meanwhile, earlier this year, something remarkable happened. Who knows what this is a picture of? Microwave background. Good. So this is, it goes by the technical name cosmic microwave background. It's a rubbish name. This is a photograph of the fireball of the Big Bang. So 14 billion years ago, there was a fireball that filled the universe. We know it was there because we've taken a photograph of it, and this is the photograph. Okay? Looking at the flickers in here really tell us most of the information we have about the Big Bang and what's happening there. Earlier this year, a team in the South Pole, this is their telescope, it's called the Bicep 2 telescope, studied a very specific patch of this sky and found something that took everybody by surprise. So they studied a patch near the South Pole, which is somewhere near here. This is the picture that they found. And so here's the picture blown up. So this is some tiny little bits of microwave background, and you can see that there are black lines that we we've drawn on this, or they've drawn on this, those black lines are polarization. So that's really what they discovered. If light travels towards you, it can travel towards you in one of two ways. It can either do that as it goes towards you, or it can do that as it goes towards you. They managed for the first time to understand in some detail the polarization of the microwave background, and you can see that there's kind of this fingerprint-like pattern as the polarization, which is these black lines that are drawn here, sort of swirls around the red bit, which is a hotspot in this microwave background. So there's something new that we've seen in the light from the Big Bang, and the question is what could cause this? So the technical name is demopolarization. What could possibly be giving rise to this swirling pattern in the Big Bang light? There's two things that we know of that could cause it. The first is that there have been gravity waves created during the Big Bang itself, ripples of space and time, which imprinted themselves on this light and gave rise to that swirling pattern. Okay? If this is true, this is the single most exciting thing I've heard in science for 20 years. I mean, it's just head and shoulders above anything else about the discovery of the Higgs boson or anything else in terms of importance. This is the most important thing that's happened. Unfortunately, there's something else that could give rise to this, which is just random dust. So, not dust in our atmosphere, but dust out there in the galaxy. It turns out as the light travels through the galaxy, this dust if the dust spins, it basically puts this little twist on the light, which gives rise to exactly the same effect, this swirling of polarization. So which is it? On March 17th, when these results were announced, the scientists who did this study had tried to understand the dust as best they could, and had decided that there wasn't enough dust to give rise to this effect. It had to be gravity waves in the Big Bang. That doesn't seem to quite be true now. The actual answer is we don't know. We don't know how much dust is out there in the galaxy, and so we don't know what's causing this swirling pattern in the Big Bang, the picture of the Big Bang. But the good news is we're going to find out. So at least within the next 6 months, everybody on the planet, everybody who cares about cosmology suddenly cares about dust. No one cared about dust before. Before something all everybody's thinking about. And within the next 6 months, we have other experiments looking at this, people doing the calculations. So very soon we're going to figure out if we've got some new evidence for gravity waves in the Big Bang, or if we just discovered some random crappy dust in the galaxy. I wanted to tell you this story because, again, when you learn science at school, it's kind of everything's figured out already, we know what's going, and it's not the case. There's so many things that we're just confused about in the universe, including dust. So I hope you all go to university, do a degree in maths or physics or whatever interests you. If you do decide to do a degree in maths and physics, the very worst thing that's going to happen to you is you're going to get a really well-paid job working in finance or IT or consultancy or something like this. But I hope that some of you after this degree will think about coming to join us in understanding what's going on here, and just being confused with the rest of us and maybe making some progress in understanding this. Okay, thanks very much.
That's all.
And the fold and cut theorem is about what you can do when you're only allowed to make one cut, one straight line cut. And it turns out you can actually do some quite interesting things. So if you start with an ordinary A4 piece of paper like this, for example, if you fold it up like that, and then make one straight cut, you can actually get some quite interesting shapes. In this case, I've got an angelfish. And I'd like to go a little bit into the maths behind this and what is possible. So while I was investigating my cutting square holes in a piece of paper, I started to wonder, is this a piece of maths that we already know about? Is this something that someone else has investigated? So I looked it up, I had a look on the internet, read some books, talked to some of my friends, and I discovered that this is a piece of maths called the fold and cut theorem. A theorem is a piece of maths which somebody has proved, and what that means is that in 1999, a team of researchers looked at this problem, which shapes can you make by folding and cutting one cut, and they discovered that you can make any shape at all that has straight line edges. And they've proved this by coming up with a method. So given any shape, they can tell you exactly how to fold a piece of paper and make one cut to cut out that shape. They've in fact got computer programs which can generate fold patterns for various different things, and what that means is that now any mathematician or any person that wants to cut out a shape can use their theorem, they can use this piece of maths to do that for themselves. I first came across this kind of maths when I was trying to cut a square hole in a piece of paper, and I wanted a hole without the square in it. And you might think that the easiest way to do that is to kind of stab a hole in the paper, cut to the edge, and then cut round the hole. But of course I realised that it would be slightly easier if I folded the piece of paper first. So if I make a fold like this, and line up the edges of the square, I now only need to do 3 cuts. Cut down here, across here, and back up again. So that's 1, 2, 3 straight cuts, and that will give us a nice square hole. But 3 is loads of cuts. I'm sure I can do better than that. So maybe if I fold it first of all in half, and again line up the edges, and then make a second fold this way. Now I've managed to reduce it to 2 cuts. 1, 2. So cut there, second cut there. And that gives me a square hole. But 2 is still far too many. I can definitely do this more efficiently. So if I take my square, fold it in half, fold this way. Now I just need to do one more fold to make these 2 lines line on top of each other. In fact, if I fold it diagonally, like this, those 2 lines are now in the same place. And if I make one straight cut, I can cut out my square hole in just one cut. Now the fold and cut theorem tells you that you can actually do that for any shape whatsoever, as long as the edges of the shape are all straight lines. And what's interesting is that even if the shape is really complicated, if it has more than one bit to it, or if it's got a hole in the middle, you can still make all of the cuts using one scissor cut. And that's kind of cool, and I think it's a nice piece of maths. So you can try and do a triangle shape. And it's actually quite a nice little puzzle to try and work out how you would fold a piece of paper. So maybe you'd fold down the middle first, because this triangle has a line of symmetry there. You could try and fold a diamond shape, which is a bit like a triangle, but more complicated. You could fold, say, a hexagon, which is going to involve a few more folds. And in fact, because you can do any shape, you can just make up your own shapes. So this is, I guess, like a ribbon shape. It's got a nice line of symmetry here, maybe another one here. Maybe that's a clue how you would start trying to cut this one out. But you can just make up any shape at all that you like, as long as all the edges are straight lines. This is the equation that describes gravity in our universe.